Welcome to the video lecture for section 4.7 on tools for counting, or sometimes we call this counting methods. In this basic introductory lecture, we'll be looking at three different techniques: the basic counting rule, permutations, and combinations. Before we get started, I want to remind you that we are building momentum towards the midterm exam. There will be a comprehensive in-class quiz on Monday. Make sure that you've seen all the video lectures before you take that quiz. There is a Chapter 4 quiz that's due over the weekend, and additional practice quizzes are available through the study plan in your online course. The midterm exam then will be February 28, and that's just 1 week from the day that this lecture is scheduled for class. We want to get started by looking at the basic counting rule, but before you do that, you want to make sure that you have downloaded and printed off the structured notes for this section. Those structured notes are available from the website for the course. It's a 4-page handout and looks something like this. The first technique that we want to look at is known as the basic counting rule, and in its simplified version it says this: if a task can be completed in 2 steps, where the first step can be performed in n ways and the second can be performed in m ways, then the whole task can be performed in n times m ways. Let's take an example of that. Let's suppose that Bob has 3 pairs of pants and 5 shirts. How many different combinations of pants and shirts can he assemble? Now, it's worth remembering that Bob is a male. It doesn't matter to him if one is stripes and the other one is polka dots. He'll put them together no matter. So Bob's strategy is this: he's simply going to choose 1 pair of pants, he's going to choose 1 of the 5 shirts, and that'll make an outfit for Bob. The number of ways that Bob can do this then is this: there are 3 ways to choose a pair of pants, there are 5 ways to choose a shirt, and therefore the product, or 15, is the total number of ways that he can choose an outfit. Now, this basic counting rule applies even if there is more than 2 steps possible. If a task can be completed in, say, 3 or 5 steps, we would proceed in exactly the same way. We'd compute the number of ways to do each one of those steps, take the product, and that's the total number of ways to do the overall task. To state that a little more formally, we say that if a task can be completed in k steps, each of which can be completed in n1, n2 through nk ways, then the whole task can be completed in t ways, where t is the product, n1 times n2, etc., through nk. Let's look at a couple of examples of that, and you'll find them on your handout. First of all, for license plates, how many are possible if we are going to use 3 letters followed by 4 digits? A couple of other rules will apply. First of all, no vowels are allowed because we don't want to be accidentally spelling words. And secondly, that the first digit may not be a 0. Well, what we want to do to solve this problem is to break this down into multiple steps. The first is that we are going to choose 3 letters. Now, for each of these 3 letters, we are going to make sure that we don't have a vowel chosen. So there are 26 letters in the English alphabet. There are 5 vowels which are disallowed, and therefore 21 ways for each one of these steps. Now notice there's nothing in the statement of the problem that says we can't repeat a letter. So there are 21 options. For instance, if you wanted to make a license plate that started with the letters T followed by T followed by T, that would be perfectly acceptable in this system. Then we want to choose a digit. However, the first digit may not be a 0, followed by 2 other digits which are unrestricted. Well, let's see in how many ways could we do each one of these 6 steps. Apparently, we have 21 options for each of the 3 starting steps because we can use any letters we want, including the possibility of repetition. For the first digit, there are 10 digits, 0 through 9, but we're not allowed to use the 0. Therefore, there are 9 possibilities for this digit. Then, there are 10 possible choices for the following 2 digits. The result is 21 cubed times 900, or a total of 8,334,900 ways to make these license plates. For the second example, we have a club which has 12 members. We want to choose people to fill the offices of president, secretary, and treasurer. In how many ways can these offices be filled if no person is allowed to hold two offices. This task can be broken naturally into three steps. Choose the president, choose the secretary, choose the treasurer. Since there are a total of 12 people available, we know that there are 12 options to choose the person for the first office. Having made that selection, and since no one can occupy two offices, we're restricted to only 11 candidates for the next, and then finally 10 candidates for the final selection, and therefore we have 12 times 11 times 10, 1,320 ways possible. Now, the basic counting rule can be combined with other facts we know about sets, probabilities, etc. So we could compute, for instance, a probability. Suppose that in a class of 40 students, we'd like to know what is the probability that at least 2 students have the same birthday. That would be the same day of the year, but not the same year. To solve this problem, it's probably going to be a great deal easier to think about the complement of the event. So we'll let E be the event that at least 2 students have the same birthday. The complement of E would be the event that no 2 have the same birthday. We'll use the fact then that the probability of E is 1 minus the probability of the complement of E in order to solve this problem. We'll compute the probability of the complement of E directly. First of all, we're going to think of the number of ways among 40 students that we could assign the birthdays in such a way that no birthday is repeated. For the first birthday, we have to select. There are 365 options in the year. There's no possibility of a repetition yet, since this is the first birthday that we're assigning. Secondly, we're going to choose a second birthday, but it cannot conflict with the first one, so we have a total of 364 possible ways of choosing. For the third birthday, there are 363, and this pattern will continue until we have chosen a total of 40 birthdays. The last one will be 326. Next, we want to divide that by the total number of ways that birth dates could be assigned to these 40 people. There are 365 choices for each of the people in the class, and if there are no restrictions, that's the number of choices we have for each of the individual students. Therefore, 365 to the 40th power goes here. Now, this value is difficult to compute directly with your calculator because you'll get an overflow if you type it in the way that it's printed here. It is possible to type it in a way, though, that the calculator can handle, and that would be to break this down into 40 separate fractions that look like this, and this will give us the probability of E. The easiest way to solve a problem like this is by using a spreadsheet, so let's open one up and get started. What we'd like to do is to build 40 fractions. The numerators of the fractions are easily predictable. They start at 365, and then each one below will have a numerator that's simply one less than the one above it. Each of the fractions has a denominator of 365, so I can build the fractions this way: equals, click on the box to the left, divide by 365, and you see our formula being built up here. I can copy that formula down, and now I've got the first 2 fractions that I need. What I want to do is construct a total of 40 of these, so I'm going to highlight these 2 cells here and drag this down until I get to row 40 in my spreadsheet. There's my list of fractions. I'm now going to compute the probability of the complement of E by taking the product of these fractions that are in column B. Fortunately, Excel has a function for that called product, so I type equals product, left parenthesis. Now I'm going to click in cell B1, press the Shift, the Control key, followed by the down arrow. that highlights all the cells that have data in them. Click up here, complete the formula by closing the parentheses and press equal. Page up key brings me back up here so I can see the product, which is perhaps surprising to be quite small. It's only about 10.9%. The probability of the event we were looking for, though, what is the probability that at least 2 students have the same birthday? That is the complement of this event, so I type equals 1 minus the probability that I just computed. Pressing enter shows me that about 89.1% is the probability that at least 2 students will have the same birthday. So the probability of the complement of E is approximately 10.9%, and the probability of E then is 1 minus the probability of its complement, and that number from our spreadsheet is about 89.1%. Let's take a look now at factorial notation. You probably noticed that we're oftentimes building patterns that look like 3 times 2 times 1, or 7 times 6 times 5 times 4 times 3 times 2 times 1. These patterns have a name. They're called factorials. The first one in our list here is pronounced 3 factorial. The second one, 7 factorial. The next one, 0 factorial, may have a surprise value to you. It's defined to be 1 rather than 0. Let me show you why that is the case. 3 factorial is 3 times 2 times 1, which is 6. 2 factorial is 2 times 1, which is 2. 1 factorial is 1. And now, how would we define 0 factorial? Well, notice that to go from 3 factorial to 2 factorial, we divide by 3. To go from 2 factorial to 1 factorial, we divide by the 2. So to go from 1 factorial to 0 factorial, it seems to fit the pattern to say that we would divide by 1, which would give us the definition that 0 factorial is equal to 1. What it does, it simply extends the pattern of divisions that make these ratios work out the way that we expect. Now, let's think of an example that we could solve with factorials. Suppose that we had 5 distinct beads that were hanging on a vertical string. In how many ways could we put the beads on the string? What we could do is apply the basic counting rule. For the first bead, since there are 5 beads available, there are 5 options for the first bead. For the second bead, then, there are 4, then 3, then 2, then 1, and the basic counting rule gives us 5 factorial for the total number of ways to put the beads on the string. Now, when we're computing probabilities, as we were in the examples with the birthdays, it's oftentimes the case that we have fractions composed of factorials. Here are a couple of typical ones: 7 factorial divided by 5 factorial, and 12 factorial divided by the product of 8 factorial and 4 factorial. I want to show you a quick trick for evaluating these fractions without writing out the factorials in their entirety. All right, let's compute 7 factorial over 5 factorial first. The trick here, we'll write it out completely this time so that you can see what's going on. 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. 5 factorial likewise is 5 times 4 times 3 times 2 times 1. Now, of course, we can see then that most of this product is going to cancel, leaving 7 times 6, or 42, for this fraction. A lot of this work could have been avoided by writing in the following way. 7 factorial over 5 factorial is the same as 7 times 6 times 5 factorial divided by 5 factorial. Having written in this way, we can easily cancel out the 5 factorials and arrive at the answer 42. A similar trick will help us move quickly through the next example. 12 factorial is 12 times 11 times 10 times 9 times 8 factorial. We stop at the larger of the two values here. Then we're dividing by both 4 factorial and 8 factorial. We can see at this point that the 8 factorials cancel out, and what remains on the bottom is 4 factorial, 4 times 3 times 2, the times 1 we can skip, and we have factors of 12, 11, 10, and 9 in the numerator. 3 times 4 is 12. Those will cancel. 2 goes into 10 5 times, and therefore we have 11 times 5 times 9 for this ratio. That number is 495. The patterns that we've been seeing to solve some of these problems could be restated as what mathematicians call permutations, the number of ways to select R objects out of a pool of M objects and to arrange them in order is denoted by either PMR or MPR. Those are two notations that mean the same things. These arrangements, these selections followed by an arrangement, is what a mathematician calls a permutation. The permutation rule says this, that the number of possible permutations of R objects selected from M is given by the formula PMR, which is M factorial over M minus R factorial. Most calculators can compute these values directly. Let's do a couple of these, both with a calculator and by hand. First of all, let's compute by hand. P75 is defined to be 7 factorial over 7 minus 5 factorial. 7 minus 5 factorial is 2 factorial, which is 2. 7 factorial over 2 is this ratio. The 2's cancel out, and we have 7 times 6 times 5 times 4 times 3, or 2,520. P12.8 is 12 factorial divided by 12 minus 8 factorial. That ratio is 12 factorial over 4 factorial. This can be computed in the same way by hand. But since there are so many factors here, let's see how our calculator can help us out. P12.8 can be computed on the calculator in this way. Enter the 12, press the math key, choose the PRB, that stands for probability menu, choose NPR, and press enter. Then enter the 8, press enter again, and we get the number of permutations of 12 things taken 8 at a time. In this case, 19,958,400. Let's just check the other calculation that we did by hand. P75, or the way the calculator takes it, 7P5. 7, math button, probability menu, NPR, and then the 5. 2,520, which is what we got in our hand calculation. Let's look at a couple of examples now that can be solved directly by permutations. The first one is this. A club has 12 members. 3 will occupy the offices of president, secretary, and treasurer. In how many ways can the offices be filled? We recognize that this is something that we could do by the basic counting rule. We would say that this task can be completed in 3 steps. There are 12 candidates for the first office, there are 11 for the second, and there are 10 from the third. So 1,320 is the total number of ways to complete this task. Now, if we solve it by permutations, we can do this with our calculator. We say we have a total of 12 people. We want to select 3 of them, and what's always important with a permutation is this, that they must be then arranged in order. In other words, it matters who we select as president, who we select as treasurer, who we select as secretary. To select the same three people, but to put them in different offices, would be a different permutation. This we could do by hand, and you can see it would generate exactly the same value of 1,320. The big advantage of writing it with permutations, though, is that I can get my calculator to do some of this work. 12, math, probability, permutations, 3. Out of 12 people, select 3 in order. 1,320 is the total number of ways. Now, permutations are not the only way that we can select individuals out of a larger collection. Sometimes it matters whether we put things in order, and sometimes it does not. The number of ways to select R objects from a pool of M objects where the order is not important is denoted by NCR or by CNR. As usual, this is the form that our calculator will use. It's the same form that our calculator uses for permutations. The number of unordered selections are called combinations, and here is the formula. NCR is n factorial over n minus r factorial and r factorial. Notice that if we ignored the r factorial, this would be exactly what we have with permutations. It's the number of ways of selecting r objects from n and putting them in order. Now, what we're doing here in dividing by r factorial is that for of those ordered selections, R things can be arranged in R factorial different ways. So we're taking the number of permutations and dividing out by R factorial to make up for the fact that the different numbers of arrangements we don't want to count this time. Of course, as with permutations, combinations can be computed by most calculators, and so let's do a couple as examples. We'd like to compute C75 and C12.8. Let's look at C75. To use the formula, we would do this. It's 7 factorial over 5 factorial times 7 minus 5 factorial. That is 7 factorial, which is 7 times 6 times 5 factorial. 5 factorial is in the denominator, as is 2 factorial. The 5 factorials cancel. 2 factorial is 2. This is 7 times 3, or 21. C75 is computed this way. 7, math, probability. This time we choose the NCR option, enter the 5, and we get 21. For C12.8, let's flip our paper over to get a little bit more room. C12.8 is 12 factorial over 8 factorial times 12 minus 8 factorial. That's 12 factorial over 8 factorial, 4 factorial. We expand the 12 factorial until we match the 8 factorial. That's in the numerator. Then the 4 factorial we'll probably want to expand out. 4 times 3 times 2. At this point, we can cancel the common factors. 8 factorials are common. 4 times 3 is 12. That will cancel. And the 2 goes into the 10 5 times. That gives us 11 times 5 times 9. Or 495. Finally, let's look at a couple of applications of combinations. Firstly, a candy store assembles sampler bags of 4 different kinds of chocolates. They have 12 different kinds to choose between. How many different sampler bags can they make? The answer is easily constructed with a combination. There are 12 kinds, and they must choose 4. C12.4 is the number that we need. That number is 495. For the second example, suppose the IRS identified a group of 25 high-income business owners in a certain area. They decide they would like to audit 10. In how many ways can these selections be made? In this case, there are a total of 12 people to choose from. 10 must be chosen. Now, if you're one of the people who are chosen to be audited, it doesn't really matter to you whether you're chosen first, second, or the 10th. You're either audited or you're not. Therefore, we would say that the order is unimportant. Order unimportant is the key to when we use combinations. Therefore, this is a combination. We have a total of 25 candidates. Of those, we're going to choose 10. Now, this number would be inconvenient to calculate by hand. We could do it, but it has a lot of factors. It's quite easy to do, though, with the calculator. 25 choose 10 is 3,268,760. This completes the video lecture on counting methods. Thanks for watching.